I promise this is now our example, more examples under our review in differential calculus. So we can start solving maybe we're done with this one, or so we can start with number 10. So number 10, this problem, a 16,823 cubic centimeter rectangular box with a square base and an open top is needed. Find the box height that uses the least amount of materials. A 16.14 centimeter, B 19.12 centimeter, C 15.13 centimeter, or D 14.36 centimeter. So this is still under optimization problems in calculus. So remember our first step in solving optimization problem. What we want is to find out what is the variable or the quantity that we want to at least minimize or maximize. So in this case, what we want is we want to minimize the amount of materials in a box. And this is not just a simple box, but it's a box that has an open top. So if we draw the box, so we have an open top box. So if we try to minimize the material, actually what we are minimizing is the surface area. So this is an open box. So we can assume that there's no anything at the top of the box. So if we solve for the total surface area, so let's just call it S, we can have a total surface area of, if this is a box, so this is side S, this is also S, and it has a height, let's say H. So if I solve for the surface area of this box, and that will be equal to, we have four rectangular faces, we have 4S times H. Then on the bottom, we have plus S squared. It's just S times H S. That's the area of the base of the box. And we don't need to include, it's not times 2 or multiply by 2. Why? Because the top is an open top. So this is what we want to minimize, the surface area. But if you look at our equation has two variables. We have S and H. So we cannot directly take the differential or derivative of this one with respect to that one variable. So we need to find a way. Again, we need to find a constraint that relates S and H. So if you look at the problem, there's a given cubic centimeter. So it's a volume. So it's a constant volume. The volume is given. It's 16,823. So we can use that one to relate our S and H. So if we try to solve for the volume, what will be the volume for this rectangular box? So we just multiply the area of the base and the height. And the area of the base is S squared and the height is just H. And we know that this is equal to 16,823 cubic centimeter. So from here, we can relate now our S and H. But remember, we are solving for the height of the box. What should be the height of the box so that we uses at least the least amount of material with the constant volume given. So we can just solve for S squared or S, and this will be equal to 16,823 all over H. Then if you solve for S, then this will be equal to the square root of that, 16,823 all over that H. And we can substitute this in our equation for the surface area. Wait, I've been using the same variable. This is a surface area. We can just call this one A, the total surface area, because I have used S for the side. And we can now substitute that in our equation here. A of S, 4 times S, which is equal to that, the square root of 16,823 all over H. and you multiply this with h. Then plus s squared, we know s squared is 16,823 all over h. So if you look at our equation now, it's all in terms of h. But before we take the derivative, we can first simplify this. We can make this one, put h inside the square root, so that will become h squared. H squared divided by h will be just h. So this will be square root of 16,823 times h plus 16,823 all over h. Then we can now take the derivative of this one with respect to that variable h. So what's the derivative? So this will be 4 all over the derivative of square root. So 2 square root of 16,823 h, and at the top, the derivative of what is inside that 16,823. Then plus, here we have h in the denominator, so we can transfer it in the numerator. It will become negative 1. So this will become negative 16,823 all over h squared. So negative 1 minus 1 is negative 2. You bring it down, it will be equal to positive 2. Then, when we are doing optimization, after we take the derivative, we equate this one to 0. That's the next step. Then solve for h. We can now solve for h. So we can cancel out 2 here, so times 2. Then solve for h. So we can also cancel out 16,823 and 16,823 at the other side. If we put the negative 1 at the right side, it will become that one. Then what will be remaining is 2h squared equals the square root of 16823 times h. We can just cross multiply that, then solve for h. So here, h will be equal to, so we can use the calculator to solve this. We have h squared at the right side, and we have square root of h. And we can actually solve that using your calculator directly. Shape calc, whatever you want, or you can do 2 minus 1 half and so on. I know the answer. The answer is just 16.14 centimeter. So the answer is 16.14 centimeter, and that is letter A. There's a shorter way to solve this one without going through this method that we did. It's calculus. It's a derived formula. You can use the formula. If you have an open box, the condition for this one to be maximum, or at least amount of material that will be used, is the side of the box or the square of the bottom of the box should be equal to twice its height. So this is the condition. You can memorize this one if you want. It's just a derived formula also. It's derived using calculus. So if you try this, if you remember this one, then S is twice H. So remember our S, and this one is our S, and our H is the height. Then if we solve for the volume, if you remember, the volume is equal to S squared times height, and we know the volume is 16,823, and S squared is just equal to 2H squared multiplied by H, and this will give you also, let me check if it's still 16.14, H squared times H, that's H cubed, so 16, so cube root of, where's that cube root? 16823 all over 2 squared, so that's 4. And the answer is really, it's also 16.14 centimeter. So if you remember that formula, you can use that if you want. But the legit way of solving this one is you can just do the normal way, the calculus way of solving the volume. Okay, so that's number 10. Let's go to number 11. So number 11, can I just zoom this one? Yan. Okay, the volume of a closed cylindrical tank is 576.56 cubic meters. Determine the tank's minimum surface area. So this is a closed cylindrical tank. So closed, it has no open sides. So if this is our tank, it's cylindrical, then the volume of this one is 500. So the volume is 576.56 cubic meters. Now, again, what we are taking the minimum or maximum is the surface area. And that's the first thing that we want to look at. So if I solve for the surface area, total surface area of this closed cylindrical tank, then I will be solving the lateral area, which is just equal to the circumference. It's just the rectangular. If we spread that out, it's just rectangle. The length is just the circumference of the circle. If this is, if we have here the radius r, then let's call the height h. So the surface area is the lateral area, which is equal to 2 pi r, that's the circumference, multiplied by h. It's the area of the lateral. Then for the top and the bottom, we add that one. That's just the area of the circle. So 2, it's 2 circles, so times 2. And the area of a circle is just pi r squared. So this is now our surface area that we want to take the minimum. And again, if you look at the right side, there are two variables that we're looking at. It's r and h. So just like what we did from the previous example, we just need to take the relationship or find the constraint between the two. And again, we use the volume of the cylinder. So the volume is 576.56. So if we use that, the volume 576.56, this will be equal to volume of a cylinder is just equal to the area of the base, which is pi r squared, multiplied by its height, h. And we can now again solve for the one variable from here. But what we are finding is the surface area. So we can just uh, find or anything. We can just solve h here. Maybe, yes, 576.5 all over pi r squared. And we substitute this in our equation here. So the area now, surface area will be equal to 2 pi or multiplied by h, which is equal to 576.5 all over pi r squared plus 2 pi r squared. Now, before we take the derivative, we simplify. Area, we can cancel out that pi. We can cancel out that 1r. So we have 2 times 576.5. So 2 times 576.5 is 115, 576.56. 115.115 3.12 divided by r plus 2 pi r squared. And we can now take the derivative because we only have one variable at the right side, so we can take the derivative of that area with respect to that variable r. And again, this is, we have r in the denominator, so we can just put here negative because the exponent will become negative 1153.12. Then you subtract 1, negative 1 minus 1 is negative 2. You put it down, then this will be r squared. Then plus the derivative of 2 pi r squared will be 4 pi and r. And the next thing to do is to equate again this one to 0. So we have 1153.12 all over r squared equals 4 pi r. Then solve for r again. So if you want to solve for r, that will be r cubed. So we just take the cube of that 1153.12 3.12 divided by 4 pi. 4 times pi. And our R will be equal to 4.51. 4.51. Then we're looking for the surface area. So we still need to solve for H. So using this formula here, 576.5 divided by pi 4.51 r squared. So we just take the square of this. So square this one, then multiply it with pi. Then this is 56. 576.56 divided by answer. And that will be 9.02. Then for the surface area now, we can solve the surface area will be equal to 2 pi times 4.51 times 9.02 plus 2 pi 4.51 squared. So what will be our surface area? This will be equal to, actually we can use this formula also. You can just use R if you want. 2 sheep pi times 4.51 times 9.02 plus 2 sheep pi multiplied by 4.51 squared. So the answer will be 383.40. This should be square centimeter because this is a surface area. This should be not cube. This should be square centimeter. Let me correct this one. Square centimeter. Because this is area. This is the surface area. And if you want again a shortcut, if you want to use a formula for a closed cylindrical tank, for it to be the minimum surface area, the condition is just, you just equate the diameter of the base, the circle, to be equal to its height. So this is just the condition. You can just make the diameter equal to the height of the cylinder, then the surface area will be minimum. Or in other words, this we can also use the radius. If you want the radius, twice r is equal to h, or r will be equal to h over 2, or half of the height is equal to the radius. So if we check that, we have our volume. Our volume is 576.5. This should be 56. 56 multiplied, this is the volume, and this is equal to pi r squared h. So pi r squared multiplied by our h is twice r. H is equal to 2r. So this will be 2 pi r cubed equals 576.56. And if we solve r here, I think it's the same r from here. If we check that, cube root of 576.56 divided by 2 sheep pi. That's 4.51. 51. And it's the same as our R in the first method that we used. So we can also use this one if it's a cylindrical tank and it's closed. Then you just equate the diameter of the circle with the height of that cylinder. Next, number 12. A building is X meters distant from a wall that is 2.245 meters high, with one end resting on the ground outside the wall. The shortest ladder that can reach the building is 6 meters long. Then what is the X, the value of x. What will be the value of x? So if we draw this, so we have a building here. This is a building. Then we have a wall that is x meters away from here. So if this is our wall and it's x meters away, so let's call that x. Then we have a ladder that is resting outside the wall. And if this is our ladder, one end of the ladder is resting outside the wall and the other is in the building. And the wall or in the ladder is 6 meters long. So this is 6 meters long from here to here. So if the wall or if the ladder, the shortest ladder that can reach the building is 6 centimeters. So this is the shortest ladder that can reach this point and the building. Now, what should be the value of x if that ladder is the shortest? That's the question. So to solve this, we can call this one h, the height of the wall. Then we can call this angle theta. So from trigo, we can say that we can call this one L. L equals 6. L cosine theta. If you take the cosine theta, adjacent side, cosine theta will be equal to adjacent side divided by the hypotenuse. So our hypotenuse will be L or d6, but our adjacent side will be this side here, x plus whatever this side here, and we can actually solve this using again tangent theta, this side here. If you take the tangent of theta, that will be equal to the opposite, which is h, divided by that side, whatever that side is. So therefore, that side is actually just equal to, can I just directly put it here, h all over tangent of theta. So that cosine theta will be equal to that side, x plus h over tangent theta, all over the hypotenuse, which is L. Or L cosine theta will be equal to x plus h all over tangent of theta. Then if I solve for L, L will be equal to x, or the right side will be all over cosine theta. So x divided by cosine theta, that will be x times cosine theta. 1 over cosine theta is just equal to secant theta. So I just write here x secant theta. And for the other one, the tangent theta is sine over cosine. Well, if we divide that with cosine, that will become just sine. So 1 over sine is just cosecant theta. So plus h cosecant of theta. Then we are solving L. Why are we solving L? Because L is the shortest. Remember, that's the optimization problem. That's the variable that we are, actually it's not a variable, it's given. But in other problems, this one is the unknown. You can also solve this using this method. So if we assume that L, again, if we take the derivative of that with respect to x is also constant. Remember, x is constant, it's not moving. So if we take dl with respect, derivative with respect to theta, we are solving for that L, but it's given. If we assume that it's not given, then this will be our method. And x will be a constant. That's the distance from the building to the wall, h. So if we take that as a constant, then this will become x secant theta. Derivative of secant theta is secant theta tangent theta. Tama. Yes. Then minus derivative of a cosecant theta is minus. So this will be h cosecant theta cotangent theta. H is also is a constant. That's the height of the wall. We are just varying the angle theta so that we can make our L the minimum. And we can equate now this one to 0. Then by equating this one to 0, we can just simplify this. We can cancel out, right? We can x secant theta, tangent theta will be equal to h cosecant theta cotangent theta. Then we can divide both sides by tangent theta. So x secant theta will be equal to h cosecant theta cotangent theta all over the tangent theta. Then next, what is x secant theta? It's just, or we can just substitute that x secant theta into this equation here. Yeah, cosecant theta. Because we have x secant theta here. So our L will be equal to that h cosecant theta cotangent theta all over tangent theta plus h of cosecant theta. But we know h and L. L is 6 and h is the height of the wall. Actually, that's given as 2.245. H is equal to 2.245 meters high. So we can factor that h and we divide it with L. So this will be 6 all over 2.245. And this is equal to, then we have cosecant theta cotangent theta all over tangent of theta plus cosecant of theta. Then we can simplify further this one. So we have the numerator, cosecant is just equal to 1 over sine. This is 1 over sine theta. While cotangent is cosine all over sine of theta. Then at the denominator, tangent theta is just equal to sine theta all over cosine of theta. And cosecant is just 1 over sine of theta. And we can cancel out other things but sine theta times sine theta, then multiply it again by sine theta here. So it will be sine cube theta. So this will be equal to sine cube theta. And then here we have cosine theta times cosine theta. So it will be cosine squared theta. Then plus sine cube theta divided by sine theta is sine squared of theta. And this will be equal to 6 all over 2.245. Then we can simplify this further. Cosine squared theta plus sine squared theta is just equal to 1. So we have 6 all over 2.245 is equal to 1 all over sine cube of theta. And if we solve now sine cube of theta or theta, we can just use our calculator to solve this. And that will be equal to sine cube if you take the cube root. So the cube root again of 6 all over 2.245. That's 1.3875. Then that's sine theta equal to that one. And we take d. So theta will be equal to sine inverse of the answer. Or wait. (1.3) it should be, because we are cross multiplying, so that should be 1 all over 1 divided by, that's sine inverse of the cube root of, we inverse that because it's a cross multiply, so it will be 2.245 all over 6. So the answer will be 46 point something. So theta is equal to 46 point. I am in degrees, so this will be in degrees. 103 degrees. So for L to be minimum, the angle should be 46.103. Now, if we solve for x, we have here, we can solve for x now. X is equal to x. We can use that formula, cosine theta, and the length is L. Then we have h and tangent theta. Or where's the better formula here? H. Okay, so this will be 6. Then just cosine of 46.103. So x will be equal to 6 cosine of 46.103. Then minus. Uh, h over tangent theta. Our h is 2.245. 2.24. So 2.245 all over tangent of 46.103. 103. For 5 all over tangent of 46.103. So the answer is 1.999999, or that's equal to 2 meters. So the answer is 2 meters. X is equal to 2 meters. And again, if you don't want to use this one, we have another formula, derived formula, that was derived from this method. And that formula is just equal to this one. L raised to 2/3 is equal to H raised to 2/3 plus X raised to 2/3. You can just directly use this formula. You can solve for whatever you want to solve here. And if you check, we're solving for X. Remember, we're solving for X. We know L. L is equal to 6. So 6 raised to 2 over 3. We know H. H is equal to 2.245. 2 raised to 3 plus X raised to 2 over 3. So if I solve for X, we can solve it directly from here. So 6 raised to 2 over 3, then minus 2.245 raised to 2 over 3. So that's that. Then we have the cube root, or we just raise this one to, we inverse that, 3 over 2. 3 over 2. So the answer is 1.99999 is also equal to 2 meters. So we can use that formula if you want. L raised to 2/3 is equal to H raised to 2/3 plus X raised to 2/3, where L is the length of the ladder, H is the height of the wall, and X is the distance of the wall to the building. Okay, next. What is the height of the tank in meters for a closed cylindrical tank with just 381.7 square meter materials and maximum volume? So this is maximum volume. Now it's given 381.7 square meters of materials. We can still use our formula before for this to be maximum and minimum surface area. Then we can let the diameter be equal to its h, or twice its radius. So this is the condition. So if you solve for the area, because the area is given, area is 381.7 square meter. This is equal to 2 pi RH. That's the lateral area plus the area of the base and the top of the cylindrical tank. Then that will be twice pi r squared. Then if you know that h is equal to twice r, this will be equal to 2 pi times 2r times r plus 2 pi r squared. So this will be 4 pi r squared plus 2 pi r squared. And this is equal to 381.7. So 4 pi plus 2 pi is just equal to 4 pi plus 2 pi is 6 pi r squared equals 381.7. So if we solve for r, that's just equal to the square root of 381.7 all over 6 pi. 6 pi. And r will be equal to 4.49 or 4.5. Is this in meters? Meters. And the height will be equal to twice that one. So 2 times 4.5 is equal to 9 meters. So the answer will be 9 meters. Then this is only true. Remember, we can only use that formula when the cylindrical tank is a closed cylindrical tank. So remember this, note, if the cylinder is closed, then you can use D equals H. But if one end is open, then you cannot use that formula or condition, but the condition will be R equals H. So if we encounter that kind of problem, if the top of the cylinder or cylindrical tank is open, then don't use D equals H. Use R equals H. Okay, next. Number 14, when the hypotenuse of a right triangle is 5 meters long, what is the longest possible perimeter? So if you draw this triangle, so given the hypotenuse is 5 meters long. Let's say this is A and B. For it to be a right triangle, the perimeter, because perimeter is, we take the longest possible perimeter. So perimeter will be just equal to S or 5, that's 5. A plus B plus 5. Then we also know the relationship, because this is again two variables and we don't want that. We know the relationship between A and B by using the Pythagorean theorem, that 5 squared is equal to A squared plus B squared. So if we solve for the other side, let's say A will be equal to the square root of 5 squared, which is 25, minus B squared. And we can substitute that in our perimeter. So this will become square root of 25 minus B squared plus B plus 5. And we cannot take the derivative here because we already have a one variable equation. And the derivative of P with respect to that variable B will be equal to this. So for the square root, again, 225 minus B squared multiplied by the derivative of the inside the square root. Derivative of 25 is 0, so minus 2 times B. Then derivative of B is just equal to 1, derivative of 5 is 0, and this is equal to 0. So we can cancel this out. Then B all over the square root of 25 minus B squared is just equal to 1. And if we try to solve for B, we take the square root, so B squared is equal to 25 minus B squared. Then solve for B. B squared plus B squared is 2. 25 over 2, take the square root of 25 all over 2. So the square root of 25 all over 2. Square root of 25 all over 2. And B will be equal to 3.54. But what we are solving is, what we want is the perimeter. So we also need to solve for A, and we know from here that A is equal to 25 minus B squared. So A will be equal to the square root of 25 minus 3.54 squared. So A will be equal to, you just take the square of this, then 25 minus the answer, then take the square root again. And A is also equal to 3.54. So if we solve for the perimeter now will be 3.54 plus 3.54 plus 5. So the perimeter is 3.54 plus 3.54 plus 5. And the answer is 12.08 meters. So that's the perimeter. Now for the formula, if you want to use the formula for the longest, so note, for the longest perimeter of a triangle, the triangle perimeter of a triangle, the triangle must be isosceles right triangle. So for it to be the longest perimeter, it should be a isosceles right triangle. So what do you mean by isosceles? Two sides are equal. So two sides are equal. So what are our sides? Our sides are A and B. So A is equal to B. A must be equal to B for it to be the longest perimeter, given that hypotenuse. So if you look at that, A here is really 3.54, and we have for A is also 3.54. So they are both equal. So it's an isosceles right triangle. So that's the condition for it to be maximum or the longest possible perimeter. Next, a 22-meter wide metal strip will be bent up the sidewalls to form a trapezoidal gutter, and what breadth across the top has the most carrying capacity if the base is 14 meters. So if you draw this, so we have a gutter, it's a gutter with a trapezoidal cross section. Now the length of the strip that is bent, this was bent. The length is 22 meters wide. And what we want to determine is the breadth across the top. What breadth across the top has the most carrying capacity? So what we want is to solve for this length here at the top, for it to be carrying the most capacity or maximum volume. So for maximum volume, we can just maximize, actually we can just, the volume is proportional to the area of the trapezoid, because the length of the gutter is constant. So the higher the area, the larger the volume. And what will be the area of a trapezoid? So this will be our base here. And let's call this one, this length here, y. Let's call it y. Then if that is y, what will be this length here? The length from here to here. If we know that it's 20-meter wide metal strip, and the base is 14, so this is 14 meters. So if it's 22, then the base is 14, then 22 minus 14 is 8, and divide it into 2, so this will be 4. and this is also 4. This length here is 4 and 4, so the total will be 22 meter wide for the metal strip that was bent. So this side at the top will be just equal to, if we can use Pythagorean theorem, this is right triangle, that will be equal to, actually that is the L, total L, minus the base. You just subtract the base, which is equal to 14, and you divide it by 2 because there are two parts, this one and this one, and this is B here. So L minus B divided by 2. This is also L minus B all over 2. Then if you solve for the area will be equal to area of a trapezoid is 1 half base 1, 1 half times base 1 plus base 2 times the height. So 1 half our base are L, and the base 2 will be just 14. That's the other base, B. Then you multiply this with the height, which I called Y. And we cannot take the derivative because there's a Y here. And there are two variables here, L and Y. So we need to relate the two by using Pythagorean theorem, the triangle around here. So what's the relationship? So 4 squared, that's the longest side, that's the hypotenuse, will be equal to Y squared plus L minus B is just equal to 14 all over 2, and we square this one. So we have an equation now that relates Y and L. So we can solve for Y squared. So Y squared will be equal to 4 squared, 16 minus L minus 14 all over 2 squared. Then we can input that in our area. Take the square root of that. So the area now will be 1 half L plus 14 multiplied by Y, which is the square root of 16 minus L minus 14 all over 2, and you square that. So if you look at the equation now, we have a single variable equation, so we cannot take the derivative. So we take the derivative of that area with respect to L will be equal to, so this is a product. So if it's a product, first, we can just remove 1 half. We put it here. Then copy L plus 14. Then multiply this with the derivative of the other one. And the derivative will be derivative of square root. So 2 square root of 16 minus L minus 14 all over 2. You square that. Then you multiply the top of this one with the derivative of the equation inside the square root. So the derivative of 16 is 0. So this will be minus L minus 14 divided by 2. You square that and you multiply, then you bring down 2. So that will be equal to 2 squared, 2 divided by 2 squared. So that will be 1 half multiplied by L minus 14. The derivative of L minus 14 is equal to 1. Then plus, so this is a product, plus, copy the second one. The second one is just L square root of 16 minus L minus 14 all over 2 squared. Then you multiply this with the derivative of the first one. Derivative of L plus 14 is just equal to 1. And we just equate this one to 0. Then we can cancel out some things. Simplify. What can we cancel here? So you can cancel that 1 half. Then we have L plus 14 times L minus 14, 1 half and 1 half, and the 1/4. So it's 1/4 L plus 14 multiplied by L minus 14. Then if you multiply these two square root, and the square root will cancel out, so this will be equal to 16 minus L minus 14 all over 2 squared. Then next, uh, here we have L plus 14 times L minus 14 is the same as L squared minus 14 squared. And for the other one, we can, at the other side, we can make this one 4, then 4 times 16, 4 times 4 squared, just make it 4 cubed, then minus this one L, we can square that L squared, minus 2 times 14, so that's 28L plus 14 squared. Then at the right side, we have 1/4, or left side, we have 1/4 L squared minus 14 squared. And we can cancel that this 1/4 here. And then what do we have here? L squared. So we have 2L squared, so twice L squared. Then 14 squared and 14 squared will cancel out. And we have minus 28L. That's minus. We put it at the other side, it will still become minus. Because minus minus is positive, then become negative. Then what else? So 14 will cancel out here. 4 squared. So we have 4 squared is just this equal to minus 4 squared, or that is 64. And this is equal to 0. Then divided by 2. So L squared is minus 28 divided by 2. That's 14L minus 64 divided by 2. That's 32 equals 0. We can actually use the calculator to solve one. And how do we do that? You go to mode, then look at equation, the quadratic equation here. So you put that 1, then negative 14, then negative 32. Then press equals. Then we have two values, L equals negative 2. The other one is L equals 16. So we cannot use the negative 2 because it's negative. We can only use L equals 16, and that is 16 meters. And that's the answer, L equals 16 meters. And we will continue this one. I'll end this one now. Continue to other part of part 2.